Assalamualaikum warahmatullahi wabarakatuh, and very good day to whoever watching this video. Today, me and my friends from group 4 are going to present experiment 6, which is torsion of bar. Our group members consist of NASREEN binti Muhammad Nasir, Noor AMIRA binti ZAMROS, DIYANAH binti RAHMAN, ALAZIM bin NOORDIN, and lastly, me myself, Muhammad FIZRI bin ISMAIL. Okay, I'm going to explain about our objective. Our objective is to investigate the relationship between torque T and the angle of twist theta of a circular cross-section specimen, and to determine the modulus of rigidity G of materials. Okay, we're moving on to the next presenter.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is NOORDIN binti Abdurrahman, and I'll be explaining the theory of this experiment. First, the shearing strain can be measured by the change in the angles formed by the sides of that element, where we can see from the equation capital L times gamma is equal to rho times theta. Then we can simplify the equation to become gamma is equal to rho times theta divided by capital L, where the symbol gamma symbolizes the shearing strength, rho is the length of the center to any point in the circle of the shaft, theta is the angle of twist, and capital L is the length of the shaft. Also, we can see that the shearing strain is maximum on the surface of the shaft, where the length from the center to any point in the circle of the shaft is equal to radius of the shaft. Therefore, we can find maximum shearing stress, which is lambda maximum is equal to radius of shaft times with the angle of twist divided by the length of shaft. We also need to consider the case of shaft of length and uniform cross-section C is subjected to torque and its free end. In the elastic range, Hooke's law is being applied when the yield stress is not exceed anywhere in the shaft. Therefore, we can find maximum shearing stress is equal to maximum stress divided with the modulus of rigidity, and also it is also equivalent with torque times radius divided with the multiplication of polar moment of inertia J and modulus of rigidity G. Therefore, we can solve for the angle of twist, which is equal to torque times length divided with the multiplication of polar moment inertia and modulus of rigidity. That's all from me. We're moving on to the next presenter.
I am Noor AMIRA, and I will explain on the apparatus used and procedure for this experiment. The apparatus that we use in this experiment is steel rod, aluminium alloy rod, nylon rod, torsion bars testing machine with load, ruler, spanner and digital caliper, just as shown in this slide. Then we will continue with the procedure. So, firstly, the aluminium alloy rod was clamped in position and the load hanger was placed on the cord. Next, the rotation scale and pointer was set at 400 mm from the fixed clamp and the pointer was set to 0. Then, a load of 40 Newton by 5 Newton increments was added and the twist of the specimen for each increment was recorded in Table 1. And after recording, the load was removed and the rotation scale and pointer was set at 200 mm from the fixed clamp. Step 1 and Step 2 was repeated. Done with the first part, the specimen was then changed to the steel rod and the procedure for the 400 mm length was repeated. The readings were recorded in Table 2. Finally, the nylon rod was clamped in position and the twist for 400 mm and 200 mm were measured, when the load up to 40 Newton again with 5 Newton increments was applied to torsion head. The readings were recorded in Table 3. The load was removed and the fully elastic recovery was observed whether it occurred or not. Lastly, the diameter of the rod was measured and recorded in the table according to the type of materials.
Hi, my name is Noor ALAZIM. So today I'll be explaining about the result for experiment 6. So we have the three material, which is the first one is aluminum alloy rod. You can see it in table 1. So we need to calculate the torque for over 400 mm and for over 200 mm. So the twist rod and the hanger load is given. So after we calculate the torque, we need to calculate draw the graph. So as we can see in the graph 1, there is angle twist versus the torque we get from the calculation. And then the second one is the steel rod. Then as same we need to calculate the torque and plot the graph, as we can see in the table 2 and graph 2. And the last one is the table 3. The same as the table 1, we need to calculate torque for over 400 mm and over 200 mm. Then we plot that in the graph 3. We get the line as the graph 3. So move to the calculation. So in this experiment, we have just one calculation which for the result data. So we have the T equal to Fr, which is torque, which is T is the torque, F is the force applied, and R is the radius of rod. So like the earlier we applied the F equal to 5 Newton and effective radius is 37.5 mm. So after we calculate, we get the value of torque. Thank you.
Assalamualaikum. My name is NASREEN AINA, and I'll be explaining about discussion of this experiment. Okay, to verify the torque of a twist formula, the graph is plotted. Based on the three graphs that have been plotted, it shows linearly increasing trends when the torque is directly proportional to the angle of twist. Therefore, the greater torque applied to the shaft, the greater the angle of twist of the shaft would be. The graph also shows that the type of material used affects the angle of twisting, and it exhibits their purely elastic behavior. Therefore, the modulus of rigidity, G, is inversely proportional to the angle of twist, as it is equal to TL over JG, where T is equal to torque exerted on the shaft, L is length of the shaft, J is polar moment of inertia, and G is modulus of rigidity. Next, the modulus of rigidity, G, for each material is determined. From the graph plotted, the slope M is equal to the angle of twist over torque. Modulus of rigidity, G, of aluminum alloy rod. Okay, M equal to angle of twist over torque. To calculate the modulus of rigidity, we have to calculate L and J first. L is given, which is 6.31 mm, and J is 155.6386 mm power 4. For 400 mm, from the graph plotted, the slope is 0.098 and the G is 15,025.8664 Newton over millimeter cube. For 200 meter, from the graph plotted, M is equal to 0.049 and G calculated is 15,025.8594 Newton over millimeter square. So the average rigidity is 15025.8614 Newton over millimeter. To calculate the rigidity of G of steel rod, the L is given, which is 4.99 mm. For 400 mm, the graph plotted, slope is 0.0106 and the G calculated is 35,520.1576 Newton over millimeter square. For modulus of rigidity G of nylon rod, the L is 6.525 mm. Therefore, J is equal to 177.9598 mm power 4. So for 400 meter cube, from the graph plotted, the slope is 0.096 and the G is 18,600 664.2965 Newton over millimeter square. And for 200 mm from the graph plotted, the slope m is equal to 0.051 and the g calculated would be 12,625.8476 Newton over millimeter square. So the average g, which is 15,645.0721 Newton over millimeter square. There are some type of experiments that we have determined, and there are few ways to overcome this error. The first one is systematic error, which is parallel errors in reading a meter scale when taking the angle of twist value. To avoid this error, our eye must be perpendicular to the meter reading scale when taking the reading. The second error is experimental error. The rod may not be kept in good condition. This can cause the rod to be exposed to heat, which makes the temperature increase and causing error in ductility. To overcome this error, the apparatus used must be kept in the right place away from the heat. And last error is external error, where the environmental error, windy environment or in the lab can cause the weight to move, making the inaccuracy of taking the reading meter scale, as the meter scale cannot stay in place when the weight is moving. And to overcome this error, we have to make sure that the experiment conducted in a closed space where there is no movement of air. That's all for me. Thank you.
Okay, hi. This is the last part for experiment 6, and I'm gonna explain the conclusion that we have came up with. Okay, as for the conclusion, we look back at our objective, which in the first place we are needed to investigate the relationship between torque T and the angle of twist theta of a circular cross-section specimen, and to determine the modulus of rigidity G of materials. All these have been determined throughout the experiment. Besides, we found out that the torque T is directly proportional to the angle of twist of a circular cross-section specimen, which means the higher the torque T, the higher the angle of twist of a circular cross-section specimen that we will be obtained. For modulus of rigidity M, the value calculated are as below in Newton over millimeter to the power of 4. For aluminum alloy rod, we obtain the value of 15,025.8614, and for the steel rod, we obtain 35,520.1576, and lastly, for nylon rod, we obtain 15,645.0721. Okay, I think that's all from me, and thanks a lot for all the viewers, and may we meet again for the next experiment. Thank you.